We've already learned to conduct a t-test for the regression slope. In this video, we're going to look at another option using an ANOVA F-statistic. So this will be testing the same hypotheses. The null hypothesis is that beta is equal to 0, so the slope is equal to 0. Sometimes we've been calling this beta 1. I should probably change that notation for the slope. So the null is that it's just a flat line, that there's no relationship between x and y, and oops, more typos. The alternative is that it's not equal to 0, that there is some slope could be positive or negative. So notice that this is two-sided. Anytime we do an F-test, it could go either way. It could be a positive or a negative slope, and we would need a confidence interval or something like that to see which direction it goes. Okay, so for calculating our F-statistic, we're going to put together some pieces from the analysis of variance table. So the numerator is going to be the mean square for the model or the mean square regression, depending on the terms you're using. And the denominator is going to be the mean square for error, or the mean square residual in other terms. So mean squares are always the sum of squares divided by the degrees of freedom. So this would be the sum of squares for model divided by p, which is the number of predictors. And we're doing simple linear regression right now, so that's just going to be 1. The mean square for error would be the sum of squares for error divided by the degrees of freedom, which would be n minus 1 minus p. So we're taking sample size into account this way. So when we put all of that together in our ANOVA table here, we end up with an F ratio of 9.3353. So I'm using the number here, and that's the corresponding p-value. The two-sided p-value is 0.0109. So since we're testing the same hypotheses that we did in a t-test for the regression slope, probably not too surprising that these statistics are related to each other. So let's compare the F statistic to the t ratio and its p-value. So our F ratio is about 9, our t ratio is about 3, and it turns out that in general, the F statistic is just the t statistic squared. So like in this case, 3.06 squared. So those are measuring the same thing. Also, we've got the same exact p-value. So these are really just two ways of expressing the same thing. So with the t-statistic, we know that the further away from 0 it is, so the larger it is in absolute value, the stronger the evidence is going to be. So if we think about squaring the t-statistic, we get the same relationship. So a larger F-statistic is going to be stronger evidence. And when we say stronger evidence, we always mean against the null and for the alternative. So stronger evidence of an association, since that's our alternative hypothesis here. So these bullet points are factors that we've considered before in the context of a t-test, but I wanted to revisit them in terms of the F-test. So I'm going to give you a chance to answer these questions again, sort of think it through again. But this time I want you to pay attention to where this is showing up in the F statistic. So not just whether your evidence gets stronger or weaker, but which part of your F statistic is changing. So as our slope gets steeper, the evidence of an association is going to get stronger. And what's changing here is our SS model. So we have a larger SS model when we have a steeper slope. So in an earlier video, we saw the SS model is just the distance between the regression line and the flat overall mean line. So the steeper your slope is, the bigger those differences, the larger your SS model is going to be. So SS model is in the numerator of our F statistic. So as it gets larger, our F statistic gets larger, and that gives us stronger evidence. What about the sample size? So as the sample size increases, the evidence of association is again going to get stronger. We've seen this in lots of contexts by now. But where this shows up in the F statistic is in the mean square error. And specifically, we're going to have a smaller MSE value, right? Because as our sample size gets bigger, that's going to make this whole denominator smaller. So remember, the F statistic takes into account not just the strength of the association, the variability explained and unexplained, it also accounts for the sample size. So the larger your sample size, the stronger your evidence. And finally, the standard error of the residuals. So the standard error of the residuals is like the spread around the regression line. And as the values get more spread out around the regression line, the evidence of an association is going to get weaker. So the standard error of the residuals is a way of measuring the unexplained variability. So as that value gets larger, this is going to be larger SSE. So SSE is in the denominator of the F statistic. So as your SSE gets bigger, your F statistic gets smaller, and that's going to be weaker evidence. So now that we've talked about how these factors affect the F statistic in general, let's look at some specific examples. So I've got 3 data sets here, A, B, and C, and the questions ask you to compare them. So which has a larger F statistic, A or B? Which has a larger F statistic, B or C? And again, think about how you would justify this based on the parts of the F statistic. So dataset B is going to have a larger F statistic than dataset A. So let's kind of compare the pieces. So the first thing that we notice is that the slope is going to be steeper for dataset B. So B has a steeper slope. And what that means in terms of the sums of squares is that it has a larger SS model. So SS model is larger for dataset B, and that's in the numerator of the F statistic. As far as the spread around the line, it looks pretty similar. I would say there's a similar spread of points around the line. And so that means that we have pretty similar SS error. So the denominator is staying about the same, but the numerator is getting bigger. So putting these two things together, I would say that dataset B has a larger F statistic. The next one is a little bit different, comparing B to C, because here they both have the same correlation, right? We see a correlation of 0.74 for each one. That also means they would have the same R squared. So if we wanted to calculate R squared, we would just do the correlation 0.74 squared, and that comes out to be 0.5476 is our R squared value. And that's for both of these graphs. So what that means is that the strength of the association is the same. We have the same strength of association. Notice this doesn't actually mean that the sums of squares stay the same. Because the sample size is bigger and sums of squares are sums, the more terms that you have in your sum, the larger your SS model and SS total are going to get. But what it means that we have the same R squared is that SS model and SS error must be increasing at the same rate, right? They're still proportional to each other in the same way, and so we have the same strength of association. So then what distinguishes these two is the sample size. So we notice that C has a larger sample size, 100 instead of just 20. So even though they have the same strength of association, C has stronger evidence of an association. And remember, when we're talking about an F statistic, we're talking about the strength of evidence, not just the strength of the association. So that means that C is going to have the larger F statistic. So it's not that R squared and F are not related to each other. They're definitely related to each other because the F statistic does take into account the variability explained and unexplained, just like the R squared statistic does. But the F statistic additionally takes into account sample size, and so that's why two data sets with the same R squared can still have a different F value.